we'll move on to the last section, which is going to include parts 3 and 4. Part 3 involves multiple object designs, and we're going to be looking at how to use a design check sheet to ensure that you've thought of the most important aspects of your design and you've gotten them written down. And this is definitely going to help you a lot when you go back to writing the final paper. We're also going to talk about how sketching out the design or creating some sort of flow chart or diagram can be very useful as a summary tool for looking at your design and identifying whether or not you have any holes in that design. So starting with the design check sheet, these are the aspects that I like to have on my check sheets. The very first thing is to record the observation that led you to undertake the research in the first place. And this section could also include a brief summary of the background and basic facts. Then comes the research problem or question. What is it that you really want to know? It's important that you don't try to test too many things in one experiment. So here's the place where you can prioritize what it is you really most want to know or need to resolve. Then your hypotheses are the possible answers or solutions that you've come up with through your brainstorming process, however you carried that out. The rationale for each hypothesis would explain why this is a potential answer to the research question. The implications of those hypotheses are going to state that if this hypothesis is true, what should you expect to have happen in an experiment? What would you expect to see? And if the hypothesis is not supported, what would you expect to find instead? Again, a rationale will clearly explain why you expect those results. Then come the details of the object protocol. First, a definition of what constitutes an experimental unit is needed. Are they real objects or facsimiles? Are your experimental units entire sheets of paper covered with adhesive? Or do you cut up a single sheet of adhesive covered paper into 10 squares, with each square then being counted as a separate experimental unit? Your final interpretations will depend on how you defined an experimental unit, and so will the design of your statistical analysis, or the decision as to whether or not you can even do any statistical analysis. Then the number of replicates is another issue you need to be clear about from the start. How are you going to define replicates? Where do you expect variation might occur? And have you defined your replicates in such a way as to be able to capture that expected variation? The measurement protocol will include the types and methods of outcome measures, such as visual evaluation, measurement of color or gloss change, etc. These should all relate back to the hypotheses and their implications. So clarifying this at the outside is helpful to ensure that you're testing for the right things so that you can clearly tell if a hypothesis is eliminated or supported, that you haven't missed measuring something crucial for making that decision, and at the same time, you may find that some of your planned tests don't really address any hypotheses and would be a waste of your time. And consider whether you can randomize a measurement order so that all replicates of one group are not measured one after the other. For the treatment protocol, it's important to clearly define your groups and controls. For example, if you're comparing the performance of two coatings for protection of silver in museum collections, say agatine and B72, and you have two different application methods, spraying and brushing, you'd likely then define 4 groups: agatine brushed, agatine sprayed, B72 brushed, and B72 sprayed. If you weren't clear about that and were thinking that you only needed 2 replicates of agatine, 1 brushed and 1 sprayed, and 2 of B72, 1 brushed and 1 sprayed, you wouldn't be able to look for differences between spraying and brushing because you wouldn't have those application methods being replicated within a coding type. So to analyze for that factor, you need to have at least 2 of each. And having uncoded controls here probably wouldn't be very useful if you can predict that silver will of course tarnish if it's exposed to pollutants with no protection, and if your main research question under study is which of these 2 codings works better. Defining your test factors means clarifying and listing the types of things you're testing. So for example, coding type, application method, metal type, etc. These are the general categories that you're going to need to be able to be crystal clear about when you're setting up any statistical analyses and making interpretations. And finally, your randomization method should be planned out. And in your final paper, it's helpful to describe what randomization method you use, because then it's going to be clear to readers that you actually did a randomization method versus the more common haphazard selection or picking of things that's sometimes called randomizing. And then what methods of interpretation or analysis do you have planned? How will you determine that the data produced by your measurements have supported or refuted your hypotheses? And you may very well need statistical analysis to get a solid interpretation. And if so, you have a statistician to collaborate with. If you do, I can guarantee you he or she will be quite happy to see this experimental design check sheet, because it'll make selecting the statistical test and setting up that test very fast and very easy. If you don't think you need statistical analysis, then what other methods are you going to use to interpret the results of your study? And finally, sketching out the experimental design or creating some sort of research flow chart can help you clarify the logic in your plan and identify holes in the design. And if you find it difficult to sketch out the design, then it may be because your design's unclear or it's too convoluted. And drawing helps you find that out before you get started on any actual experimentation. And sketching out the design of the experiment, of an experiment that you're reading about in the published literature, I find also is helpful, because it'll help you better understand exactly what they did and how they carried out the work. For example, here's a sketch for a simple experiment that was comparing the aging performance of 4 adhesives. Each experimental unit here is defined as a sheet of paper with adhesive applied. 4 replicates were desired for each adhesive. Color measurements are to be taken before and after accelerated aging, with color change and yellowing quantified. In addition, peel strength is to be measured, and because this test is destructive, an additional 4 replicates are going to be prepared for the initial before aging tests. The final after aging tests can be done on the original 4 replicates after the non-destructive color change and yellowing measurements are completed. So we could describe this particular experiment as having 1 test factor, which is type of adhesive, with 4 treatment groups. And none of them being control, since paper alone without any adhesive isn't likely to be informative. So instead, we probably likely are including at least 1 adhesive that's already routinely used in conservation and comparing it with the performance of at least 1 newer adhesive being proposed for similar uses. Even a very complicated multi-year project benefits from a research design sketch, and you don't have to try to read all the detail here. This is just a sketch to illustrate a large project I planned out and submitted for funding. Many of the proposal reviewers mentioned that there was a lack of clarity in the research design. So of course, naturally, my first instinct was defensiveness. Of course, the research design was well thought out and clear, but obviously it wasn't clear to the readers. So I realized that I had violated my own rule. I hadn't sketched out the research plan. And so I figured, well, I'll just sketch it out, and that will help readers more clearly see my brilliant research plan. But in my attempt to sketch it out, I realized that the readers were actually right. There are a lot of holes in the research plan. So after a lot of revision and rethinking and replanning, I was finally able to sketch out a research design that clearly shows a central research question, a primary hypothesis, 9 sub-hypotheses, and all of the tests that will be used to see if these hypotheses are negated or supported. And once I'd written out this sketch, then it was a lot easier to describe the research plan in a way that was much more clear to reviewers. Many experimental designs that we use originated in agriculture, where a lot of research has been done testing variables such as seed varieties, pesticides, watering practices, that sort of thing. A typical design used in agricultural research is called the split plot block design, where multiple agricultural fields are used for testing, with each field divided into sections so that each factor is tested both within a single field and between fields. And this makes for a very robust and reliable comparison. This is a very appropriate design for conservation research, and it's sometimes seen in the literature. A very good description of the experimental design elements for this type of design is given in this paper by Green and Lease that appeared in Studies in Conservation. We'll go through exactly how this project was set up. They started with the initial observation that paper often becomes acidic over time, and that this is caused by multiple factors. Hence, deacidification is carried out to stabilize the paper. Often an aqueous solution can be used, but if you have water fugitive media present, a non-aqueous solution may be needed. And at that time, the British Museum where they worked was using a solution of barium hydroxide and methanol, but this wasn't considered satisfactory because it was toxic, and the treatment produced an initially high pH within the paper, which they're afraid could cause hydrolysis and damage the cellulose change, although the pH did gradually decrease in exposure to air as the hydroxide was converted to carbonate. So the research problem here was that additional non-aqueous solutions were needed. The main hypothesis to be supported or refuted was that methyl magnesium carbonate could be a successful alternative non-aqueous deacidification agent. And the main rationale for that is that it's non-toxic, and also it decomposes. The decomposition to magnesium carbonate occurs rapidly on exposure to air, so they thought maybe that the paper would not have this initial high pH and that this should hold up over time. So the treatment, an implication would be that the treatment would not show adverse effects on tensile strength of the treated paper, either immediately after treatment or after accelerated aging. Experiments were done on 2 types of paper, Whatman filter paper and 19th century printed book pages. So here the experimental units were defined as including both facsimiles and real objects. The larger papers were then divided into sections for treatment. So these are the plots, which makes it analogous to agriculture. There were 3 replicates for each combination of factors, paper type and treatment type, and there were 7 treatment groups: a commercial methyl magnesium carbonate and methanol, methyl magnesium carbonate prepared in the lab in methanol, barium hydroxide in methanol, calcium hydroxide in distilled water, and this was included because it's another comparative standard treatment that would be used as an aqueous treatment. A control that was treated with only distilled water, another control treated with methanol alone, and an untreated control of just paper. So there are 2 test factors, paper type and deacidification method, and here the randomization method was clearly and explicitly described. Measurements included pH measurement by surface electrode and tensile test to check for paper damage. And both of these measurements were done before and after a period of accelerated aging. Interpretation of the data was by statistical analysis using analysis of variance. And they were able to conclude that the effects of methyl magnesium carbonate on loss of tensile strength and pH were similar to that produced by barium hydroxide. However, the new treatment has the advantage of much less toxicity, so it turns out it could be a very good alternative treatment. Now, this last design included two factors, paper type and adhesive type, but we can increase the number of factors to some extent, provided there's good reason, which means we're giving clear rationales for every factor we're adding in, and as long as we don't let it get too complicated. As one example, I had a recent project with the goal of developing protocols using software for image analysis for ceramic thin sections that could reliably and reproducibly measure the area percentage of sand-sized particles in the fired clay. Rather than start with unknowns, which would have been real archaeological ceramics, we prepared test tiles in the lab using known proportions of clay and sand, and with purchased sand that had a known particle size. Since image analysis tends to vary for different basic appearances, we used two types of clay typically found, with one that fired to a red color and one that fired to a white color. And since we thought protocols might show some variation depending on particle size, we used three sand sizes: fine, which was 70 mesh, medium, 30 mesh, and coarse, 16 mesh. The sands were primarily quartz, and each of these were added to the clay in three different target proportions: 10%, 25%, and 40% by volume of loose sand mixed into the wet clay in the same manner that a traditional potter might add in temper material. We prepared 5 replicates of each combination of clay type, sand size, and sand amount, and this is because we felt that it was likely to be a lot of variation. There are also 3 replicates for each clay type with no sand added as our controls to check for any natural sand that might be present as a background. After drying and firing the tiles, small slices were cut from each, and a thin section made for each of the 96 tiles, and these were mounted on glass slides with a blue dyed epoxy so that quartz grains could be easily separated from pores for the image analysis, because in plain polarized light both would appear clear if we used clear epoxy. The thin sections were scanned in a high-resolution film scanner at 7 microns per pixel, and then the images used for image analysis, and we used a software package called Image Pro Premier by Media Cybernetics. The protocol that then proved to be fastest and easiest to accomplish while giving accurate and reproducible results was then applied to real archaeological ceramics. Now, since the amount of sand added to the tiles needed to be known for our protocol development, one way to incorporate blinding and randomization into the process was to check on the results once the protocol was finalized. Then samples could be randomly reanalyzed without knowing the added sand amounts or which ones were replicates of each other or what any of the previous analyses were. So randomized and using blinding. And then these results were compared back to the original results. And when excellent comparability was found, that could increase our confidence that the protocol was actually ready to apply to real archaeological samples of unknown sand contents. And this is one way we can sketch out the experimental design with this whole combination of factors. We have the white clay and the red clay, and we have 10%, 25%, and 40% added sand using different symbols. And then we have the fine, medium, and coarse sand shown by different size of each of those symbols. But if we try to get too complicated with too many factors, sketching and even planning for and keeping track of all the many combinations would get extremely difficult. For example, if we try to run an experiment testing coatings on metal, and we want to test it on several metal types: sterling silver, fine silver, copper, lead, bronze, and brass, perhaps of varying surface shapes, flat and curved, and then we want to test for several different methods of surface preparation. several coding application methods, perhaps several different thicknesses as well, all for 9 codings or so. Things are quickly going to get very complicated to try to interpret. And it's likely we're going to find at the end when we're trying to do our analysis that we didn't actually keep all of these variables in mind, and so we didn't get good replication of each. And even then, trying to discern which variables are really important for the final results is going to be difficult. We'd be better off to do one experiment with the most crucial variables, such as metal types and coating type. And then for those coatings that appear promising for specific metals, we could do another experiment to refine things regarding the effects of surface preparation, application method, or coating thickness. One major problem with maintaining silver objects in historic houses or in museum storage and exhibit spaces is that many construction or decorative materials that might be used somewhere in the vicinity of silver off-gas hydrogen sulfide. And even very, very small concentrations of this pollutant is going to begin the tarnishing process and can quickly turn silver black. Regular cleaning of your silver artifacts is not a good solution because that's very staff intensive in time, and each cleaning is going to remove some silver and will eventually create damage to the surface. An example of an elegant, well-designed and well-described experiment in conservation that was intended to address this problem can be found in a paper by Grissom et al., published in the Journal of the American Institute for Conservation in 2013. And it focuses on evaluation of coatings for the protection of silver exposed to hydrogen sulfide. One thing that makes this an elegant experiment is that they kept the focus on the most important factor for preventive conservation of historic silver collections, the ability of coatings to protect silver from hydrogen sulfide exposure, which is by far the most problematic pollutant for silver. They didn't try to also test the effects of other pollutants. They kept things simple so that the most important factor could be clearly tested for. So they used only sterling silver coupons of one size and shape. They didn't also try to test fine silver or to add in copper or lead or any other geometries. They tested 12 coatings. All of them were given a stated rationale for why that particular coating was chosen for testing. They selected one standardized application method. Then each coating had 4 silver coupon replicas, and the thickness of the coatings was measured with repeated measurements along the coupon. Coupons were exposed to hydrogen sulfide for 125 days with periodic removal for continuous evaluation because they wanted to capture when change initiated for each coating. Randomization was performed wherever it was appropriate, such as in the selection of spots for testing and in the order of coupon placement within the hydrogen sulfide chamber. Coatings were evaluated by visual observation, image analysis of digital photos, gloss measurements, and colorimetry. Each step of the experimental design is very clearly described with all rationales, implications, and measurement and treatment steps described with enough detail that there's no need to guess as to what was done and why. And as a result, some clear and useful results were obtained that are going to help move conservation practice forward. And it would also be easy for anyone else to replicate the study or to carry it further. While there are many possible variations in experimental designs, what's most important to keep in mind are the basic ideas of aiming for a simple, elegant experiment that will provide clear results rather than trying to do too much in one experiment and having very confusing results. Keeping focused on the original observation that led to the research, on having a clearly defined research question or problem with clear hypotheses, implications, and rationales stated, defining the experimental units and having appropriate replication, keeping clear what the test factors are and then restricting these to the most important, carrying out randomization so that uncontrolled factors can be spread around and not affect interpretation of results, and then using statistical analysis where needed to aid interpretation. So I recommend this paper as a good model for an example where all of these issues are very clearly stated. We'll move on to the last part here, where we're looking at, first briefly at single object studies, and then at some variations in experimental designs. Well, replication is usually important to identify variability and to make sure that results of an experiment or study are generalizable to some sort of larger population. Sometimes you may have only a single object available for study, and generally this is going to be the case when you have a real cultural heritage object that you're working with, since experiments with facsimiles can pretty much always be replicated. And with a single object study, you may primarily be interested in making conclusions that are best for the treatment of that one object. So here the generalizability to other objects is of secondary interest. The most important tool for being able to design a statistically valid study using only one object is to find a way of randomizing treatment in your control areas within the object. So in essence, you're making an object its own control by treating it more than once using a formal experimental design. You set up a design whereby there are several times or places at which one might apply the treatment, and then random assignment of treatment to one of those times or places gives an experimental design that can be used for statistical analysis. It has probability, and especially if you can include blinding, then you have a really good study. This is simply an extension of the idea of test patches, but instead of haphazardly testing a few patches on an object, you randomize which patches receive one or more test treatments and which remain as controls, and this allows you to reliably compare the results. For qualitative assessments, it's even better if the assessment can be done by someone who's knowledgeable enough to be able to make the judgment, but who doesn't know which patches received which treatments and which ones are the controls. For quantitative results, you now have the statistical probability assumption met, and so you can reliably do statistical analysis for comparison. An analogy is seen in medicine in the idea of test patches for testing a person for allergic reactions. While there are also larger scale experiments about general causes of allergies, number of people in a population who tend to have allergic reactions to specific food items or other types of exposures, and the range of allergic reactions, when an individual person is having a problem, they see a physician to receive tests about their own very specific allergic reactions. Test patches might be defined on their arm or their back with patches numbered, and then the numbers used on a coding sheet that gives information about what possible allergens were applied to which patches. Placement is often randomized with replication, and then the results are assessed by the patient or by a physician blindly with respect to knowledge about which allergens were used in which patches. A case study of a single object in conservation that followed this sort of formal design is a paper by Eric Hansen and Stan Durillian, and it focused on an 18th century tapestry woven in wool and silk that was installed in the Huntington Library between 1911 and 1920. Their observations included that it was very dirty and it needed to be cleaned, but the silk portion was dry and brittle to the touch. So while the effects of aqueous solutions or dry cleaning solvents on the physical and chemical stability of silk hadn't yet been well investigated, there had been some reports of negative effects, especially of repeated aqueous treatments. But another tapestry in the group that had been recently cleaned using a standard wet cleaning technique with a non-ionic surfactant, that one they found that after washing and drying, the silk appeared very differently, it seemed actually to be more supple, with less breakage and less damage on handling. So their research question then was, does cleaning cause a significant difference in tensile properties of silk? The main hypothesis was that silk threads could be more resistant to fracture after washing. The implication or rationale for the hypothesis were, first of all, that tensile properties of silk change with the pH. Second, reintroduction of water to dehydrated silk fibrin might affect tensile properties. And third, silk may undergo physical aging, but those changes might be reversible if it's plasticized by water to the extent that the glass transition temperature is depressed to near room temperature. Here, the experimental units were defined as threads from one real 18th century woven tapestry that had never been treated before, using multiple threads taken from within this single tapestry. So a grid was superimposed over the tapestry, and then a number was assigned to each coordinate on the grid. Then, using a random number table, threads were randomly selected for sampling. Replicate sampling was done with before washing, where part of a thread was sampled, and then after the tapestry was washed, they returned to take more sample from the same thread or from an adjacent thread. And in sampling, single threads of 2-ply weft were unwound at the random locations, and about 5 millimeters was removed. So they had ended up with 20 paired samples of before and after treatment. There were 2 treatment groups defined, treatments and controls. So the controls were the samples taken before any washing occurred. The treated samples were those taken after the entire tapestry had been washed. So the test factors were washed or not. Measurement for effects was done by tensile testing, and then interpretation by statistical analysis using analysis of variance. The results showed that the threads were actually significantly stronger following the washing procedure. So the results pointed toward the need for more basic research into the effects of washing, and they felt this could be especially relevant to handling of archaeological textiles in situ. They did recommend that there should be a further study on long-term strength or other potential negative effects of washing other than the ones that they tested for, and the effects of washing on other factors such as dyes. However, because they kept their experiment simple without trying to pull in all of these other potential factors into one single experiment, they were able to get clear and useful results. In preservation, single object studies can also include a survey or assessment of the potential degree and type of problems found in a library or a library system. In this case, the library itself is conceived of as a single object, and the results are intended to primarily provide conclusions needed for making treatment plans within that one library. So we're not trying to generalize to other libraries in general. Here, the observation might be that deterioration is a crucial problem in large libraries where there's a mix of age and type of collection items. So then the research question might be, what are the preservation and conservation needs of this particular library? The experimental units would be real books from that collection. And the number of replicates that you would need is likely to be pretty large because you can expect a lot of variation. If you think about all the different potential types of items in the collection, bound journals, older deteriorated books, new books, lots of different sorts of things. So in order to capture the full range of variation, you're going to do a lot of replication. You could use randomly selected a random number generator that could use your already existing call numbers on file. And if there are different types of collections, you could do stratified random sampling. If you have sub-libraries, such as different compartments. It might be under different environmental conditions. Again, you could do stratified random sampling amongst those. And then this design could be used for observational types of surveys where you're qualitatively assessing for each sampled book certain things such as is the primary protector intact or not? Are the printed pages intact or not? Does there appear to be environmental damage such as fading or water damage or not? Is there immediate treatment needed, and if so, what type? To get an overall profile of the deterioration present and the preservation needs of this library. It could include some very basic quantitative data such as pH, but probably basic descriptive statistics such as calculating percentages of each category of deterioration is likely to be sufficient for your analysis. But the main thing that would be needed for reliable results in this case would be to ensure that all of the assessors receive joint training so that you're going to have consistency in the qualitative judgments. The use of randomized selection and high replication for each potential type of library materials also means that you're going to have results that are likely to give you an accurate picture of the preservation and treatment needs of that library. A haphazard selection of books is just never likely to give you accurate results because there are a lot of things that can go wrong. But if you think, for example, if you were to assign the staff to select haphazardly 1,000 books, some might walk along the aisles and pick things that are easily accessible. Others might be drawn to things that have more attractive covers. Somebody else might think they should be selecting the older, worn-out looking books. Others might be attracted to selecting the newer books. But either way, you can't assume that the selection is going to be truly representative of the amount and type of problems found in the collection. Now, a conservator is not likely to want to design a true single object study for every object that's treated. But sometimes you're going to be working on an important object for which there are at least 2 treatment options, and you're going to want to be able to reliably choose which of those and have confidence in your results. And you may want to feel that you can prove to the owner or curator that in fact the best option was indeed chosen. So in this case, it could be worth spending the time to define multiple patches, do randomization, and have a more formal test. And strictly speaking, the results of a single object study are only applicable to that object. However, the more reliable conclusions can give you a more solid foundation for planning a treatment for that object. And another advantage is that over time, a series of completed single object studies may lead to more general conclusions. Screening experiments are often used in medical research. For example, to do initial screening of a lot of different compounds that might be useful in fighting cancer. And then those that appear promising are pulled aside for more intensive, in-depth research. This will be a very quick testing. You don't do replication generally in screening tests. So they're useful for formulating hypotheses, identifying possible treatments, but it always requires follow-up testing with replication before going forward to anything to do with treatments. I've tried out a rapid corrosion test that was originally developed in industry as a quick screening test for potential corrosion inhibitors. So here a small amount of water with an inhibitor is held against the surface of the metal for 24 hours. The ability of the inhibitor to prevent corrosion is assessed visually or quantified by image analysis, and then anything that looks promising in this screening could then be used for more in-depth testing and evaluation by a variety of other analytical tests that would take a lot more time and a lot more expense. Somewhat different goal for a screening test is described in a recent Studies in Conservation article written by 2 conservators. They developed a rapid, simple test for detecting chlorides that can be used during conservation surveys of collections that have a lot of porous materials such as stone, ceramics or unfired clay objects such as cuneiform tablets like we see here. These are situations where a large number of objects have to be evaluated very quickly and at low cost. So they developed a quick test with a soft brush. A small amount of surface dust is transferred from the object to weighing paper and then into a vial containing a silver nitrate solution. A white precipitate that's best seen using your smartphone light will form if chlorides are present. This test is intended to quickly confirm the suspicions of an experienced conservator and detect surface chlorides that sometimes might otherwise be overlooked. And then more precise quantitative tests that take a lot more time and money could be added in for a selected smaller number of objects as a backup confirmation test. But having this simple, low-cost, rapid screening test available can improve the conservator's confidence in their observational results and improve decision-making in setting treatment priorities. A treatment trial is another type of study, and the last one that we'll talk about, and this one is developed in medicine. Medical and conservation research share the problem that the usefulness of laboratory experimentation is limited. Eventually, treatments have to be carefully tested in the context of a real practice on human patients for doctors and cultural materials for conservators. And this will almost always mean the introduction of additional uncontrollable variables, but the results for careful experimentation with real subjects are usually a lot more applicable to treatment practice in general than the results of less realistic laboratory tests alone. In medicine, the physician is the PI, or at least a co-PI, rather than or in addition to a scientist, since only the physician can determine the treatment for a person, the best treatment, and only the physician can actually perform the treatment on that person. And in our case, the person who can best make the treatment decision for an object and carry out the treatment is the conservator. The scientist can't do that. The medical profession has put a lot of effort into perfecting and refining the optimum treatment trial procedures, and I think we ought to be able to benefit from that experience. Treatment trials are really a response to ethical concerns of applying treatments. The author of a book on treatment trials in medicine, Clifford Minert, and his book is on your reading list, notes that the history of medicine is filled with drugs, devices, and other treatments that were originally announced as great advances, but which later are shown through treatment trials to be useless or even harmful. And these mistakes include thousands of prescription drugs reviewed by the FDA, with about 1/3 of them found through treatment trials to actually be ineffective, even though they looked very promising in laboratory and animal studies. And so for this reason, the medical profession has devoted a lot of effort to developing and refining the concept of the treatment trial. And I think it's really the basis of modern medicine. And today, no drug can be approved by the FDA until it has been documented to be effective and safe in at least 2 separate clinical trials. But clinical trials don't mean just haphazard application of treatments to see what happens. There are certain protocols that must be present for a valid clinical trial. It's a planned experiment that takes place in a clinical setting rather than a laboratory setting, using multiple patients exhibiting the same medical problem. And important aspects of a treatment include that both groups, your treatment and your control, are going to be treated and followed over the same time period. And that takes away a lot of uncontrolled factors that might show up if you try to use historic studies. The control can either be no treatment or a standard treatment that's already known to be effective and safe. And the trial has to include enough patients so that you can adequately evaluate the results. Most clinical trials compare 2 treatments and average about 25 patients in each group, and this number is both generally practical and doable in terms of time and resources. It's also very important to clearly define the class of patients, or in our case it would be objects, eligible for the study, so that other researchers can assess whether or not the results apply to their patients or objects. But if you restrict eligibility too much, for example, instead of saying we're going to test photographs with mold, if you restrict it and say we're going to test albumin prints produced in a given 20-year period with a particular species of mold, it's going to get more difficult to come up with enough objects within a reasonable period of time, and that might end up requiring a multi-institution trial. The important components of a treatment trial are things that should all look familiar to you now, because these are the same things that are important components of any other sort of experimental design. You have randomization, blinding, controls. You've described your treatment protocols in detail. You have good measurement protocols that are going to be relevant to testing your treatments. You have adequate sample size and replication. You're going to be describing your implications and rationales for these at every stage. How the treatment trial is formulated and evaluated is really interesting. It's constantly reassessed and reevaluated through specialized journals on the methodology of treatment trials in medicine, and there are also thick books focused only on clinical trials, and they provide discussion about even the smallest detail of a clinical trial design. There's also the Society for Clinical Trials that helps to provide constant evaluation and improvement of methodologies. For example, some issues they consider include additional design thought that has to go into the process if you have multi-center trials versus single-center trials, if these are needed to increase sample size. With multiple centers and a lot of different people involved, it becomes extremely important to have detailed forms for patient evaluation with training sessions and pilot studies to make sure that everyone's following the same consistent protocol before beginning a larger study and more expensive clinical trial. If you think back to the that study of milk with school children that I talked about, if they had done a pilot study before they launched into their study of 10,000 treatment children and 10,000 control children, they would have very quickly found that there was a major problem with allowing teachers to undo the randomization and make their own assignments, and they could have found that out before doing the entire 20,000 children study. Books such as these also note that it's crucial to avoid having to change your forms and procedures midway through the trial. So again, a pilot study will help you refine what your procedures are. But if you didn't do a pilot study and you're partway through, it's better to just continue the way you started, because you can always do a follow-up trial in a different way if you've changed your mind partway through about what should be done. They also talk about the need to avoid undisciplined data collection. The idea that while we're at it, why don't we record everything we can think of to say about each patient or object, because someday we might want to ask additional questions about the data. And that you shouldn't have too many secondary projects going on. What often happens with clinical trials, if the main question is you're trying to do a trial for cancer cures, for example, sometimes one of the investigators is also interested in using that same set of patients to study the relationship between smoking and baldness. Another wants to look at coffee drinking and high blood pressure, etc. This very quickly becomes too complex, and you lose track of the original questions and data that you're trying to collect. So you also don't need to worry too much about whether you're going to have sophisticated instrumental analyses. If the research questions can be answered through simple observations and simple measuring techniques, that's fine. What's important is good design, appropriate treatment protocols, and outcome measures, and clear analysis of results. So basically we're looking at the same sorts of issues that are needed in any experiment. A simple, elegant one that gives a clear result is always best, and overcomplicating, trying to do too much in one experiment, tends to produce unclarity, and this just becomes even more important when you have multi-center treatment trials where many researchers may be involved. Now there are obstacles to applying this to conservation, and in fact I'm not personally aware of any true treatment trials having been carried out in conservation or preservation. I've seen a few studies labeled treatment trials, but these have not contained the research design elements that I've just mentioned. One problem may be funding, because true treatment trials usually are going to be multi-year projects. And if they require participation and coordination of multiple centers so that you can enroll enough objects into the project, then that requires even more funding. And this level of funding is harder to come by in conservation than it is in medical research. The NIH and drug companies will fund large-scale, multi-year treatment trials, but that's difficult to find funding for in conservation. But I think they could be a very useful tool to add to the experimental design arsenal of cultural heritage, conservation, and preservation. So this concludes our survey of scientific method and experimental design in preservation and conservation research. Thank you for your attention, and I hope to be reading about many more wonderful research designs in future coming from you. And we'll conclude. Oh, I also want to thank NCPTT again for hosting this webinar and making it available. If there are any additional questions,